So this is a presentation on topological classification of time oscillations. It's using topological data analysis methods to classify periodic and non-periodic time series. So the motivation is that detecting periodicity in time series is applicable to many different scientific fields. This includes identifying brain oscillations or detecting gravitational waves. Traditional methods usually parameterize periodic components in time series in the frequency domain and power spectral density functions, and this composes signals into sine waves. But this might not capture the complex non-sinusoidal features that are typically found in brain oscillations or these gravitational wave examples. So in this approach, we introduce methods for classifying time series as periodic, oscillatory, or aperiodic, non-oscillatory, using the methods from topological data analysis class. And we'll follow this pipeline. So first, all the data that we'll be discussing is synthetic, so it's simulated, and we generate periodic and aperiodic time series and their corresponding autocorrelation functions. Secondly, we create persistence diagrams for both the time series and these autocorrelation functions, and convert these diagrams into vectors using metrics like amplitude, persistence, entropy, and simply the number of points in the persistence diagram. Then we will train a logistic regression classifier using the extracted features from both the time and autocorrelation domains. And lastly, we evaluate and compare the classification accuracies of these methods in distinguishing periodic from non-periodic signals. So this slide is relatively technical, but a concrete starting point for this project is just to look at simple linear time processes, specifically autoregressive order 2, AR2 processes. So as a training data set for classification, I just simulated a number of AR2 processes because the choice of the theoretical parameters lead to well-defined oscillatory or periodic dynamics. And the behavior of AR2 processes depends on the value of these phi coefficients, and we can classify them as either periodic or non-periodic based on this theoretical boundary. So sampling coefficients below this boundary leads to periodic time series. Coefficients above this boundary is non-periodic time series, but within the whole triangle, these processes are stationary. Okay, so another more technical slide, but in the time domain analysis, we apply Takin's embedding theorem to transform each time series into a higher dimensional space. However, in the results, it looked like the noisy embeddings infected our results. So this indicates a need for more robust methods. So here are the definitions, but more of an intuition is here are 5 columns. Each is an example of an oscillatory AR2 process. So the coefficients are sampled from below this oscillatory boundary. You can see the second row is the time series has periodic components, and then the Takin's embedding is the row below. It's clear that there's cycles and circles in the embedding, but they are quite noisy, so it would be difficult to pull out any like large-scale loops or patterns in the series using these persistence diagrams. Okay, and here's the same example, but now these are non-periodic time series, so the coefficients are sampled above this boundary. And similar, things just get quite noisy. Okay, so another technical slide is the autocorrelation domain. This helps deal with some of the noise because they're averaging over many time points, and we use sublevel set filtration then on these autocorrelation functions to capture topological features of the autocorrelation function. So this approach showed a significant improvement in the accuracy compared to the time domain analysis. It highlights the importance of autocorrelations in detecting periodicities. So here we define two methods. We look at the sublevel set filtration directly on the autocorrelation function, as well as the Takens embedding of the autocorrelation function in the Torus-Rips filtration. So here's the intuition. These are the same 5 oscillatory time series I showed before, but you can see that the first row, the autocorrelation function, is much cleaner. There's less effects of noise. If we apply sub-level set filtration, we can see directly the critical points of these function, which is what marks the oscillations. Also, if we apply a Takens embedding, you can see that the oscillations create a spiral to the origin, and also identify that the persistence diagrams are different between different time series, especially if we compare them now to the non-oscillatory examples. Okay, and the last step then is to, from these persistence diagrams, to featureize them. So we can apply these features to a downstream classifier. So we use the methods available in this Python package. Specifically calculated the amplitude, the distance between persistence landscapes for each of the 2 homology dimensions in these diagrams. Persistence entropy was calculated as the Shannon entropy of points on a persistence diagram. And then we also just simply calculated the number of points on the off diagonals of the persistence diagrams here. So here are the results. The simulation setting generated time series of length 200, autocorrelation functions of length 50, and 5,000 total time series. So these are sampled both from the periodic and aperiodic regions of the AR2 stationarity triangle. And half of them were below this partition, half of them were above. And we just use a simple logistic regression classifier with features from the previous step, and both broke it down into a training and validation set. And then measured the performance of the classifier using accuracy and area under the ROC curve as performance metrics. And the results showed that the autocorrelation domain, particularly when combined with Takens embedding and Vittori-Rips filtration, performed best in classifying time oscillations. The accuracy was around 90% in both the training and validation sets. So in summary, this project demonstrates the effectiveness of topological data analysis in classifying time series as periodic or not. Our findings underscore the importance of different preprocessing and feature extraction methods in topological data analysis that can be used for time series classifications. Just to point out this third point here, that the best performance occurred when mapping the time series to multiple stages, so from time to autocorrelation, then to embedding. So this looked like it captured the most robust topological features of the time series. All right, thanks for listening.